So our next research fellows is going to then be talking about products of hydrogen. There it's Usman's back on the floor again as well. Thank you.
Sure. Hi, I'm Usman Ali, and I'm also working on utilization of co-products of hydrogen production. And this is project 7 of our REHIP scale. And what the scope of this project, that we all know that there are different colors of hydrogen, and we are investigating blue, green, and turquoise hydrogen. And along with hydrogen, we are getting different co-products. If we talk about blue hydrogen, we are getting a good amount of CO2. Of course, we are putting in pipeline and then storing it, but we can also have a use of CO2 in food industry and other aspects where we can utilize that CO2. In a similar fashion, for green hydrogen, we are getting a good amount of oxygen as a co-product. What kind of technology is adopted? We are testing different technologies for each of the color of hydrogen. And similarly for turquoise hydrogen, just to narrate it, turquoise is by the pyrolysis of hydrogen, in which methane is broken down into carbon and hydrogen, and we get carbon black as a co-product, and which is used as a filler in our storage industry and other industries. In addition to all these elemental co-products, we're also getting a good amount of waste heat in all of these processes, and we can utilize that waste heat in a multiple fashion in heating purposes, or and one innovative aspect of this project is that we are utilizing that waste heat with metal hydride compressors, which is a motionless compressor, in which we can compress the hydrogen to the required pressure of our consumer. So we can utilize all of the co-products of different colors of hydrogen in our businesses, and also we can utilize the waste heat either for the heating purposes or other industrial purposes, or the community heating, and we can also use it for the industrial purpose on the same scale that we can utilize it for metal hydride, which is a novel technology in which we can compress hydrogen or separate hydrogen from methane. In doing so, we are also doing technoeconomic evaluation, and we are developing that how these co-products will benefit us in reduction of the cost of the main hydrogen from different colors of hydrogen. We are investigating these 3 colors. We can go for the other colors, but for this project, we are sticking to blue, green, and turquoise. So for blue, we are investigating steam methane reforming, in which methane reacts with the steam to produce a synthesis gas, which is a carbon monoxide, carbon dioxide, and hydrogen, and we do multiple reactions and separations, and then we do CO2 capture for the system, and then we have pure hydrogen from our system. A new technology under discussion is also autothermal reforming. We also investigating in thermodynamic simulation that what kind of different co-products are generated. For clean hydrogen, we are investigating alkaline and PEM technology for hydrogen production and co-products, and for turquoise hydrogen, which is pyrolysis of methane, and we are investigating the thermal, because pyrolysis is a thermal process and it requires a lot of heat. But if we put some catalyst in it, the amount of heat requirement reduces it. So we are going for both thermal and catalytic systems to check how much carbon is produced along with hydrogen, which is the main product actually. And in parallel, we will be checking the demand and supply of different co-products, especially in T-side industry cluster, that how we can map these co-products of CO2, carbon, oxygen with our different industries, and how it will benefit for our businesses in T-side, and by evaluating through techno-economic evaluation, and we will be developing through a visual interface that if we're getting a good number of carbon, or with time, and we have good installations of different kinds of hydrogen colors, and then through this visual interface we can see that how these co-products are benefiting us in terms of businesses across the T-side industry cluster. So this visual interface will be a MATLAB or some tool through which we can check, put the numbers in terms of demand and supply. In parallel, the innovative aspect of that project is the metal hydride compressors. We'll talk about how it works and what kind of things we are doing on it, in which we use some solids which can absorb hydrogen and then generate hydrogen at higher pressure. So we can also do the separation, and this is a motionless compressor actually. The moving parts are not there, so we can compress hydrogen at the last stage of our any of the scheme of hydrogen for hydrogen production. So in terms of initial mapping, if we see, we have put blue, green, and turquoise just randomly and see that we can put CO2 into pipeline. We can put CO2 for our food industries. We can utilize the CO2 for our CF fertilizers if they have the purpose to produce ammonia or urea from it, because we can use CO2 with ammonia to produce urea, which is a fertilizer for us. We can use oxygen from our green hydrogen for high temperature combustions or for welding purposes. Carbon is a filler which can be used in our packaging industry. Carbon can be used for treatment of the wastewater, activated carbon. So this is how we can integrate different businesses from our hydrogen production scheme. And we will be doing complete mapping on it for T-side industry cluster, that how these co-products can be integrated with different businesses in our system. We have industry partner TVC here, from which we will getting those numbers in terms of demand and supply and other aspects. So at the moment, we are modeling the blue hydrogen for both steam methane reforming and thermal reforming, depending upon the capacity that we have seen with respect to hydrogen T-side project. We have fixed the same capacity of 250 million standard cubic feet per day, and we are installing the similar units like PSA, special absorption for the purification of hydrogen to reach the composition of our requirements. Either is to be used for industry or is to be used for fuel cells, depending upon the use. The hydrogen purity, we're fixing it to be 99.9%, and we are using 6-stage compressor so that we can have a CO2 in a supercritical condition, so that we can compress it and put it in a pipeline. If there is no use, and we can put it through NEP pipeline into our North Sea. We are using the natural gas composition which we have in the grid, and the air composition which we estimated across the year to our data. Based on that, if we talk about the blue hydrogen, we generally get CO2 as a co-product. And CO2 can be put inside different usage in terms of transporting it to the North Sea. And if we talk about the pipeline requirements, we generally have 95% to 97% CO2 purity. The other components vary depending upon the operators of the pipelines and other components based on which we can tune it. So depending upon the PSA, number of PSAs that we install. And we also have the usage of CO2 in liquefaction plants, where the requirements of greater than 99% because of hygiene and other aspects for food and beverages are required. For liquefaction, we generally keep greater than 99% because during liquefaction, if there is water, it creates issues. So that's why for liquefaction purposes of the CO2, we have to reduce the other components to less than 1%. So this is how then we keep the number so that we can have the required purity depending upon the requirement of the user, and to tune our model in such a way so that we can reach the purity of our consumer. So if we talk about the blue hydrogen for steam methane reforming, this is a general plant layout for steam methane reforming. This is a similar plant that we have for BP for gray hydrogen at the moment. We all know that for sulfur removal, we generally do the removal of sulfur from natural gas, the first thing that we do in our steam methane reforming. Then we have 2-stage reforming, generally primary and secondary. The first stage is for higher carbons, and the second stage is for pure methane. And we convert more than 98% methane into synthesis gas. And then we do the shift reaction in which we convert the remaining carbon monoxide into carbon dioxide and hydrogen. And then we have the separation. If you see, there are 2 CO2 capture systems, one across the line of synthesis gas and one across the flue gas, which is being used for the reformer for the heating purposes. So both have a different composition, so we cannot mix them. One is hydrogen rich, one is CO2 rich. One is flue gas that is obtained after the combustion of natural gas. So we have to install 2 different CO2 capture systems if we are going with this SMR technology. And after that, we have to install pressure sink adsorption and CO2 compression, 6-stage compression as per the requirement of the pipeline. If it is for liquefaction or other purposes, we may not require CO2 compression in those stages. And lastly, we have to compress it towards the requirement of the consumer. In terms of ATR, ATR is a new technology in which we do not require any external heat or external combustion of natural gas for the reformer. Or that's why it's called autothermal. That means all the heat is being managed automatically within the reactor. And we are managing it by changing the composition of our feed, natural gas and steam. And instead of air, we are using oxygen. And we require air separation unit for our autothermal reforming. That's an additional thing that we require. However, the added benefit is we have integrated management of the heat within the reformer. Plus, the other things in terms of kinetics are similar. Of course, conversion and other aspects are changing in terms of kinetics. But we are getting two reformers with added technology in terms of heat management. We do shift actions in which we convert carbon monoxide into other aspects, but we only require one CO2 capture system. That means we do not need any CO2 capture system for the flue gas. We only require CO2 capture, which we have conventional for our ammonia or urea systems or petrochemical industry that we can install on our thermal reforming to capture the CO2 from our synthesis gas and then put it to compression, and we can then purify the hydrogen by PSA, pressure sink adsorption, and pressurize it. We did these models similar to our actual plants in our software, which is a chemical process simulator S1 Plus, and we keep the capacity of the same as of hydrogen T side, and the purity of 99.9% by PSA. And for CO2 capture for SMR, we have installed two, one for flue gas, which is MEA, monoethanolamine, one of the conventional system that we install in our power plant. The same is going to be installed for CCGT carbon capture, MEA-based CO2 capture system. And for synthesis gas, generally recommended in fertilizer and petrochemical industries, MDEA, same is being installed in hydrogen alone projects that are being used for the production of blue hydrogen across the world, in Canada, France, and USA. The three projects that are already installed are using MDA technology. The percentage of CO2 capture varies depending upon the requirement of our CO2 capture and target of our the technology installer. The CO2 compression is 6-stage, and we are getting the four products, which is CO2, with approximately 1.8% increase in CO2 if we are installing ATR, and we are getting nitrogen as a co-product for ATR because we have an air separation unit in our ATR. So that nitrogen can also be used or integrated with businesses in the T-side industry cluster. And that nitrogen purity is 99.3% from our autothermal reforming process. So these are numbers in terms of how we're getting per year, approximately 2.27 metric tons of the CO2 we are getting from SMR, and 2.34 approximately, they are the same number. We are getting CO2 from either SMR or ATR, but for ATR we are getting nitrogen in a good amount, and in ATR we get a good amount of heat as a co-product, which can be utilized for low-grade heat or medium-grade heat, depending upon what part of the plant we are integrating it with the community, or for industrial heat in terms of steam generation and other purposes. We are working on it, and we will be developing models for green and turquoise hydrogen, and we will be doing the techno-economic analysis in the next part of the system. And that's another part of this project is metal hydride compressors, in which we can utilize the waste heat of our hydrogen production steams to compress the hydrogen. And what is metal hydride compressors? Metal hydride compressors uses metal hydrides as a solid adsorbent, in which hydrogen is adsorbed in a cyclic manner, and then it is being released at a high pressure. And because its temperature and pressures are being involved, and key benefit is that we do not have any moving parts. We only have a solid state, so safety aspects are good in that compressors. So we do not involve any moving machinery, and the efficiency of this compressors, this kind of compressors are good, and generally it releases hydrogen at high temperatures and high pressures. So our design is to integrate metal hydro compressor at the Durham University with a small electrolyzer, and check that how we can utilize that excess heat of our electrolyzer to compress the hydrogen, and check with what kind of different solids behaves on that manner. And for that electrolyzer, we are experimenting with PEM system. So we will be doing capacity calculations for the selected metal hydrides, and this is a test rig that we have developed in Durham University. My co-worker Mehdi is doing that work, and we will be performing adsorption and desorption tests for this kind of experiment. So that's all from my side. Any questions?
So Mark Smith again from North Standard Marine Insurance. Part of the concerns we've noted in the industry with carbon capture is the quality control of the carbon capture and the end user. Is that a concern for this project, or is it not something that is a concern? You know, that's just something we've heard from the industry. That's perhaps a concern when ships are going to be using carbon capture and landing at a shore, that they're unsure of the quality controls in place, because obviously some end users may have very strict criteria.
We can tune the quality of the CO2 that is being put in the pipeline or being used at scale. That's why I've indicated the CO2 percentages for different aspects, for the liquefaction or for beverages industry. We can tune that number, but at the end, it depends upon the industry which is going to operate that plant, actually, what the requirements are and how they can tune it, because whenever we are tuning towards the lowest numbers, we require a lot of inventories in terms of solids and the solvents for the systems, and which generally is the cost.
Yeah. Thank you.
The metal hydride, you're looking so into literature review, actually testing the different types of metal hydride, the temperature, how this fit with the different electrolyzer, and let's say the availability of the metal as well.
To my understanding with Mehdi, they are selecting metal hydride from the literature survey, and then they are testing that metal hydride with the available electrolyzer at Durham University to the low grade heat that we have from electrolyzer, and that's how we can integrate that heat with metal hydride to compress the hydrogen.
Because I guess there's gonna be, let's say, if it's PEM or alkaline, you choose a different type of metal hydride because of the temperature.
Yeah, because metal hydride varies with the temperature and pressure requirements. Yeah, that's why the initial screening is literature survey, that what kind of metal hydrides will be compatible with that amount of heat, and then we will test those numbers. Yeah.
So yeah, very quick question. It might be a daft question, so feel free to shoot it down. But when you talked about the different processes there, so there was ATR and the other one. Apologies, I forgot the acronym. Is there a big cost difference between the two? Is there a reason why you use one or the other than they produce different byproducts?
The cost difference is there, plus technology difference is there. The ATR is an efficient technology and emerging technology in which we have a good amount of heat integration. There is less waste heat from our system. We are not doing external combustion. So in terms of efficiency and in terms of that numbers, ATR is a better technology. And we are getting multiple co-products from ATR if we compare in terms of co-products. Yes.
Just a quick question. I want to know what are the heating and power requirement for the CO2 capture unit, and why you choose two different types of working fluid for the CO2 capture unit?
For heating requirements for the CO2 capture system.
In terms of kilowatt for your system.
We use steam, and it varies depending upon the percentage for both SMR and ATR. Depending upon what percentage of CO2 you see, there are different numbers of CO2 for both SMR and ATR. And we have two CO2 capture systems for SMR. And so the heat varies for each CO2 capture, And the exact numbers I don't remember at the moment. I can give later.
And
looking
another
into
question,
simulation.
why you are not calculating the efficiency?
We are calculating the efficiencies for gas efficiency for the system,
All right.
and however, just we haven't put it there. Secondly, because why we are using different technologies, ME and MBA, because flue gas has generally for natural gas combustion, the CO2 is 4 to 5% CO2 for natural gas combustion, and for our synthesis gas, we have a hydrogen which is 60% pure hydrogen. We don't want to mix that hydrogen with 4% flue gas, which contains only 4% CO2, rest nitrogen, oxygen, and water. So that's why we keep both lines separate. One is hydrogen rich line, one is CO2 rich line. And then we put two different CO2 capture systems. Of course, capital cost or fixed cost will be high, but our operating cost will be much less.
Thank you very much.
Great. Is there any other questions we finish off with? Right, well, thanks very much, Usman. Thank you.